This session, what we'll be doing is we'll be talking about the use of climate scenarios, how they can be applied. We'll just spend 5 minutes or maybe 5 or 10 minutes on that. Then we'll go into a bit of detail on what are these particular scenarios saying. I hope we can have a good conversation around that and questions that you have about the scenarios themselves, because I do think that that is really a super interesting topic and one that has relevance not only in our work, but of course, as people living on this planet, there's certainly a significant degree of relevance to what these scenarios say and what they demand of us. I'll talk a little bit about the assumptions. So when you're looking at scenarios, you know what matters and what doesn't matter. There's, I think, 1,729, maybe it's now 2,600 and something, some massive number of variables in the new NGFS scenarios. But which ones really matter? Which ones are the ones that define the scenario, that make it relevant and important for you and your understanding? So we'll talk about all of that, and then we can get into some conversations around scenarios and climate modeling itself. So this is going to build a bit off the conversation that we had yesterday at the back end of the strategy discussion. But as I said, I'm super excited to talk about this. You can probably tell it is one of my favorite topics to cover, because I just do think that these scenarios are so interesting, even for their limitations and challenges. The fact that we are probing those limitations and exploring them is itself a useful and valuable exercise. And so it's not to say these are projections or forecasts, but rather that we can still learn a lot by exploring them. So anyway, to jump in on applications, we talked a little bit about this previously, but this question of why use climate scenarios? What's the point? There's a lot of things we don't know, and why are climate scenarios useful? And what's really valuable about them is there are so many unknowns in the climate system, from climate sensitivity to what policies different societies undertake, to the rate of development of technologies, to the responsiveness of certain aspects of the climate system to different feedbacks. And so the reason that we look at climate scenarios is because they can provide a highly complex and simulated world that we can understand and we can look at and really begin to say, hey, this is something that is meaningful and something that is useful for us to try out our views, even if we don't think it's the most likely. So it's not that any one of these paths is definitive, but it's that by looking at different ones, we learn certain things. So in this case, what you see is this relationship between the rate of emissions. As I mentioned, there are 4 main scenarios. There are the RCP 2.6. Those are scenarios that typically are ones that are strong emissions reductions over time. Then there's 4.5. Those are ones that are more moderate reductions. Then 6.0 tends to be a little bit of a low action or low climate action scenario. And then 8.5, we actually see continuing emissions rises without a real leveling off. And that is really seen as a worst case scenario. It's unlikely that we will continue to grow our emissions. It's more likely that we will either flatten or decrease them. And yet at the same time, understanding what physical impacts can happen at some of these worst case scenarios are useful for our risk planning. Understanding what levels of transition risk result in 2.6 from the really rapid cuts to emissions are also useful to understand. So when we're talking about these scenarios, the value is not only that they can give us insights into the physical world, but also into the degree of transition challenges that we are potentially going to face. We talked a little bit about this yesterday, but recognizing this idea of a kind of 2x2 matrix for climate scenarios depending on the transition path chosen, we're going to face different challenges in the future. Those challenges can be in terms of physical challenges, so damages from physical phenomena, or they can be transition challenges, shifts in economic structures that are either destabilizing or disorderly. And ideally, we want to proceed on a route that is going to be as orderly as possible while limiting warming. And that's what are considered the orderly scenarios. They're immediate, but while aggressive, gradually increasing actions to limit both transition and physical risks. A disorderly transition also gets us to our goal, but we get there in a far more bumpy way with a lot more economic damage on the route. We'll talk about both of these because there are examples of each of them in the new NGFS climate scenarios that we'll cover. Also, there's a need to think about this question of challenges in terms of what if we start too late and then take climate action? We could get some of the disruption and some of the physical damages. And then finally, at the end, on the hothouse world, this assumes that limited actions are taken. So we maybe don't face as abrupt and aggressive a transition, but we don't do much to avert physical risks. So we see rising risks throughout the scenario. So the importance of these is that they really represent to us different paths that we can follow. So when we're looking for decarbonization pathways, we want to be choosing ones ideally that are orderly. When we want to be doing risk analyses or stress testing, disorderly scenarios may be better. When we want to assess the physical hazards in a location and ensure we're protected, then perhaps a hothouse world scenario is useful. And so each of them, while they reflect different, more optimistic or pessimistic futures for us, have their uses. So as I mentioned, orderly can be very valuable for target setting, disorderly for stress analyses, hothouse world for physical risks and physical impacts. And as we go on, we've talked about how climate scenario analysis can be used. Yesterday, we talked about in strategy setting. Also, of course, given that this is a course on the TCFD, they also relate to TCFD climate and other climate disclosures. Having scenario analyses is a key part of the forward-looking metrics that are increasingly specified by these standard setters. They can also be used to convey internal information in the direction that you're heading in terms of the key risks that are coming up. They can be used to set policies. So if we're trying to stay under a given threshold, what does that mean for, say, origination limits? Also, what about for limits and on the other side of that, targets? If we're looking at a net zero target, what does that mean for our rate of decarbonization? What does that mean for the amount of industrial companies that we hold? What are their intensities of emissions? These are all questions that scenarios can help us to begin answering, even without telling us definitively the answer. They show us a path and a path that we can prepare for, or a path that we can draw insights from. So as we go on talking about the scenarios themselves, we can see that there's a wide application. And this is really not just thinking about the short-term scenarios, but also longer-term ones. So we have both the macroeconomic short-term scenarios and those longer-term scenarios that go out 30 years, or going back here a couple of pages, all the way out to 2100 even. And there may be questions, well, why look at 2100? What's the point? And the point really has to do with the fact that many of the decisions we make around technological investments and developments will have ramifications, as will climate feedbacks in terms of the conditions that are faced in the farther future. And so the decisions we make now will have impacts and influences on these particular challenges. And that's really the key here, is to explain that both a long-term lens and a short-term lens are going to be necessary in scenario analysis and assessment. So to go into a bit more detail on the applications, as I said previously, In terms of the strategy disclosure, disclosure C covers this specific point about describing the resilience of an organization's strategy, taking into consideration different climate-related scenarios, including a 2-degree or lower scenario. So that's getting to some of the points that we were just discussing and just covering around the need to use scenarios to look at different futures. The graph you see here is from the NGFS and looks at both CO2 as well as all other greenhouse gases, and shows the rate of decline under its orderly scenarios, its disorderly scenarios, and, as I mentioned, those hothouse world scenarios, the ones where there's limited action. Scenarios are a powerful tool because they can help us explore the effects of policies. And indeed, these scenarios were created initially not for the financial sector, but for policy makers, with the idea of showing how different policies change the incentives economically around certain energy systems, around certain economic behaviors. They also can explore how different rates of technological development and different cost curves for certain technologies have impact on the uptake. So in a very, very simple statement of these models, they are optimization engines. They are aiming at a goal, in this case, a temperature target, and taking in all of these other parameters as a way to get there. And as a result, they're helpful in thinking about different policies. They're also helpful in building a foundation to think about how policies are likely to affect their sector or even their business specifically. If you're looking at a scenario that is forecasting a 70% contraction in your sector, how do you ensure that you are not part of that? Or how do you ensure that your business is resilient to that change? On the other side, if you are in an area that is expected to get hit by stronger storms, what does that mean for the insurance coverage you purchase? What does that mean for the resiliency plans you offer? All of these can be thought about through scenario analysis. In addition, scenario analysis is, as I said, used by regulators. In this case, what we see is from the recent Bank of England climate stress test, there is the expectation that those that are supervisees will use these scenarios. And similarly to what we mentioned before, there are 3 types of scenarios: early, late, and no additional. These correspond to the orderly transition, a disorderly transition, and a hothouse world. And so in a lot of ways, even down to the specific variable values, they've taken the NGFS scenarios and applied them here. And that was something that the ACPR in France and OSFI and the Bank of Canada did in Canada in their exercises, which was take the NGFS scenarios and use them as representative in these climate stress tests. So what you can see here is another application for the scenarios, of course, which is in stress testing. So the question I think that emerges is, how are these scenarios put together? Where do they come from? What are the assumptions made? And we'll get to those assumptions soon. But before we do, one of the keys is to understand the models that are generating them. These are called integrated assessment models, and they're called that because they integrate multiple submodels or subcomponents that speak to each other in ways that enable interactions and optimization to occur. They can be deeply complex in a way that allows you to understand dynamics of complex systems like economic systems. They also are able to, while being complex, need to make simplifying assumptions about certain things. So energy systems, what technologies are available? The land system, what types of land use are there? Farming, forestry, industrial use. What are these types of simplifying assumptions? And then also from a climate perspective, what climate engine are we using to assess climate sensitivity? So as temperature increase, or as carbon dioxide increases, how much warming do we get for that? So all of those are pieces that go in. The climate information, the specific policies you want to try out, assumptions around technologies and drivers, and what you get out is a spate of time series variables, a real set of energy variables, land use variables, emissions and investment related variables, as well as information into prices and overall levels of demand for other goods. So the key here is that these scenarios are generated by a complex machine. The advantage of that is it allows you to do these complex what-if questions. The downside is that there are lots of stylizations needed, both for the energy system as well as the climate system, in order to make those decisions and make it computable. You may have heard of some of the main integrated assessment modelers. I'll go through this list here. Most of the integrated assessment modelers, and this goes to that question from yesterday about validation, which is most of the integrated assessment modelers are part of a consortium called the Integrated Assessment Model Consortium. That consortium is one that works on advancing the state of climate science and also freely and in open source fashion enables the use of the code for these different models for public use. When we look at the integrated assessment models, there is the WICH model, which is developed by an Italian team. There's the Remind model developed by the Potsdam Institute, also known as PEAK. There's the GCAM model, which is by Pacific Northwest National Laboratory and the University of Maryland. There's also IMAGE out of the Netherlands, MESSAGE, which is out of Vienna, the International Institute for Applied Systems Analysis, and then AIM, the Asia Pacific Integrated Model from the Japanese National Institute of Environmental Studies. When we're talking about the NGFS scenarios, we're referring to models that have been specifically selected by them, not necessarily because they're better, but rather just because that's who they had chosen to partner with. But we'll be looking at the GCAM model, the MESSAGE model, and the Remind model. So those are the University of Maryland and PNNL, MESSAGE from YASA, and Remind from the Potsdam Institute. And those are ones that I think will be ones that you may hear about again or see again. And in some ways that should give just an overview of kind of who is in this landscape of climate modeling. Let me stop here just to see what questions you have around scenario use or around climate models before we go into the specifics of the scenarios. So once again, returning to the Network for Greening the Financial System, the work that they do on scenarios is really held and done by their macro financial work stream that's led by the Bank of England with heavy involvement from Banque de France and also the DNB in the Netherlands and the Bank of Canada. They also have other work streams that look at supervision, at green finance, data issues, as well as additional research topics. At this point, they represent nearly 100 global regulators on 6 continents. They are really focused, though, on increasing the relevance of climate scenarios in the financial sector by improving their standardization and comparability. And that's really the fundamental elements of this, this exercise on their work, is to ensure that people use the scenarios, that supervisors use them for assessments, that individual institutions apply them. And in this latest version of scenarios, they aim to address some of the outstanding challenges that existed from their first set. And so we'll talk about what these new scenarios entail, as well as what some of the old issues were that they confronted. So each NGFS scenario is different, and each one of those three modelers that I mentioned, YASA, Peak, and University of Maryland, each run these six scenarios. So essentially there are 18 model runs that are there. And the differences between them will be based on differences in assumptions of technology, differences in assumptions around climate sensitivity. But in many ways, you can kind of triangulate the outputs by looking at what the three pathways say, and where they converge can be an important point to say that even with somewhat different assumptions, there are only so many ways of getting to a given climate goal. So just to note, what you're seeing here are the Remind model outputs. That's the one from the Potsdam Institute on the screen, but that doesn't mean that those are the only ones that can be generated. As I said, both the YASA models as well as the University of Maryland models also have these same scenarios and same variables. So we just talked previously about that kind of 2x2 of possibilities for transition risk and physical risks. And then we also said that within that, there are 4 different dynamics: high physical risk, high transition risk. That's called too little, too late. That we don't see as one of the 6 scenarios they've chosen. They choose instead from the other 3 buckets: high physical risk, low transition risk, that's hothouse world; high transition risk, low physical risk, that's a disorderly transition; and low transition risk, low physical risk, that's the orderly transition. So within each, they've provided 2 scenarios, one kind of a primary and one a secondary. So the primary one is net zero by 2050. Net zero by 2050 hits that 1.5 degree target that science says is necessary to remain at, and does that by getting to net zero carbon dioxide emissions rather than greenhouse gas emissions, but carbon dioxide emissions by 2050. The below 2 degree scenario is similarly a positive scenario for climate progress, but is just simply less ambitious and thus reaches a higher overall temperature. It's going to be less of a challenge for institutions on the transition side because it's going to have that transition happen slower. And you can look at the blue line in the left graph versus the green line to see what I'm referring to. For disorderly scenarios, we have the divergent net zero, which is another way to get to net zero. But in this case, what happens is the rate of policy development is uneven. So certain parts of the world experience higher carbon prices and have to act more quickly, where others take their time. And that creates imbalances in global trade. It creates various other international challenges to globalization. So that has a more negative drag on the economy. You also have a delayed transition, which assumes that even though we know climate action is necessary, we don't take strong action for the next 9 years. And then at that point, we've used nearly all of our carbon budget. So the only way to hit a reasonable temperature is to rapidly cut emissions. And in this case, we still don't hit 1.5, but you can look at how steep that light green line is, even compared to the net zero scenario in terms of emissions. It stays high for longer, but then has to fall very sharply. Finally, there are 2 of the hothouse world scenarios. One is the nationally determined contributions. This is everything nations have pledged to do. And you can see that that still doesn't get us below 2 degrees. So that's when people are saying, oh, the Paris commitments are insufficient. That's what they're referring to. And then in a even worse case, if we did nothing today beyond just let the market develop the technologies to expand renewable technologies, to expand electric vehicles. And we said, we're not going to take any action to change the pace of this rollout. Then we'd be looking at just our current policies. And that's going to result in about 3 or more than 3 degrees of warming. And we're not going to see much of a significant reduction in CO2 up to 2050. That case will be a very minimal transition risk, because the only risk will really be coming from replacements on a technology level of expensive fossil fuel technologies with cheaper renewables. Now, for each of these scenarios, to talk through them in a little more detail, I think it's really helpful to think about risk drivers. And specifically, the risk drivers that exist are ones that are related to certain attributes of the scenario. In this case, on the physical side, the degree of physical risk relates directly to temperature. We know that there's an inverse relationship between temperature and physical risk. The higher it gets, the hotter it gets, the more physical risk there is, the less the temperature. Flip that around. It's a positive relationship between the two, negative relationship between the level of policy ambition and the degree of physical risk. So what this is showing is lower temperatures are going to have lower physical risks. On the transition side, the speed of the policy transition can indicate how much risk you're likely to face. The level of technology change can be potentially disruptive, even if that is a positive. And then in terms of carbon dioxide removal, the more carbon dioxide removal you assume, the lower, the less you need to cut emissions today, because they can be removed later. So all of those are, I think, important points to make. And finally, as I said, divergencies in regional policies means there are opportunities for arbitrage, or also for trade wars to take place, or taxation of imports. And in some ways, that is significantly more inefficient as well. At the same time, it recognizes that there is a need to be equitable in the development of policies, because not every part of the world is at the same place, nor does every part of the world need to take the same exact actions to decarbonize. So one last slide before I take some questions about the NGFS scenarios, which is what we see here, essentially, that there are new expectations for energy investment. And this is relatively similar to what we saw in May when the IEA came out with its own scenario, that there's quite a lot of investment in green energy that is absolutely critical to make this transition happen. It's not just enough to tax, it's not just enough to make fossil fuels unprofitable. We still need to meet our energy needs. And the only way we're going to do that is through really strong investment. And you can see that investments in fossil fuels need to fall. But you can also see, importantly, that green energy needs to be significantly larger as a share. And if we add all of these up, it's a relatively similar dynamic to what the IEA had suggested. They had suggested about 4 trillion a year for clean energy. This suggests somewhere around 3 to 4 trillion as well. And what is the result? Well, the result is, look at the ordinary transition going on with these red bars. The ordinary transition here is moving from relatively small share of our fuels being renewable to about 25% by 2050. That's progress, but it's not fast enough. If we look to the rightmost graph, we can see those red bars getting much bigger. That's essentially making the assumption that nearly 75% of our energy, and more than 75% if we include nuclear, needs to be coming from renewable sources by 2050 in order to meet our decarbonization goals. So one question about the NGFS is it only used by the financial sector, or can all sectors use the tools produced? And the answer is all the sectors can definitely use the tools. What the NGFS has done is it's created a number of open source tools that are particularly helpful. There's a scenario explorer. There's also through the YASA website a more detailed investigator for looking at individual variables and scenarios. But I would say that if I had to give coverage numbers for the different sectors, I would say the energy sector tends to have a lot of really detailed variables. Transportation tends to have pretty good variables. Buildings and property is moderately covered. Same with metals and mining, same with industrials. Agriculture tends to be more lightly covered, not that it's not comprehensive, but that it's not as detailed. And then other sectors such as services and technologies tend to be lumped in as end use sectors because they don't contribute typically quite as much to emissions. But somebody looking to set a net zero target for their business can use these scenarios to do so, even if they were developed by a group of financial regulators. So one question is about divergent. What does the divergent net zero scenario mean? So let's go back a couple pages. Essentially, the idea of the divergent net zero means that there's significant regional variation in the rate of climate policy, and also significant divergence in the speed of decarbonization across sectors. So you may have rapid decarbonization in one sector, but that may not be ideal because it might be a factor input into another sector. So perhaps there's rapid shutdown in oil and gas, but maybe that's not so great for transportation because they haven't fully shifted over to electric vehicles. We can see in the divergent net zero that the policy happens immediately, but it happens unequally in different sectors and different regions. And we can see some variation in the degree of change by region. So I'm going to give just a quick overview before we open for some final questions, because I do want to give a bit of time to answer any questions you might have. So I'll move somewhat quickly over these, but there are a ton of variables and it can be confusing. And these big models, sorry, must have clicked off my screen. There we go. And these big models can be intimidating and confusing. Like there's a lot of pieces. And I think very often people say, I don't get it. I don't understand how they work. And in some ways, as users of the models, it's important to understand their assumptions even more than their dynamics, because those are assumptions that should be familiar to you from your business experiences. And if those assumptions don't jive with your assumptions, that's an area where you can think about, are there overrides? Is there skepticism that I should apply? Are there other scenarios that better explain my view of the world? So I think a lot of people get bogged down in the complexity of the models, but I would say there are really only 4 or 5 key considerations that I think everyone should know about. First being socioeconomic. And the reason this matters is population and GDP growth. All of these things matter because all else equal, more people means more food, means more land for agriculture, means more energy. A richer population needs more energy, will be consuming more, will put greater demands on food systems and industrial systems. So all else equal, the rate of growth of population and the rate of growth of GDP tend to be a middle of the road projection. So they've looked at what the World Bank and the UN have said for these, and that typically is the common engine in most models. If you tweak that or you play with that, that's going to have different impacts on how much of a cut is needed. If you assume a world in 2050 of 11 billion, not 9 billion people, then the energy demand is also going to be significantly different. So the ease or challenge of reaching some of these climate goals depends on the socioeconomic assumptions. I see these as kind of the background, or sorry, the backbone of the scenarios. The next piece are policy and technology assumptions. And while there can be many of them, fundamentally they all break down into two types. One, how aggressive is the action on climate? And that can be literally in the sense of carbon price. So how expensive is emitting carbon? Or it can be in terms of, on the technology side, how fast is the rollout? How quick is the fall of cost for a given technology? How much is that technology expected to contribute to the total energy mix? So different models will be more bullish or more bearish on certain technologies. Different models will call out stricter or more immediate policies, but you'll look at those to say, the higher the emissions price, the stronger the policy, the more potentially disorderly the transition. The faster the technological rollout, the bigger the possibility for disruption of incumbents, but also the cheaper, the longer term aspects of the transition will be, because costs will be driven down by, in the economic terms, learning by doing. Another key assumption is carbon dioxide removal, or what's called negative emissions. One of the big changes has been for these models, and in the IEA, it's also similar, relatively low deployment of negative emissions technologies. That's important to note because previously these models had found that negative emissions technologies were one of the cheaper ways to remove CO2 from the atmosphere and deal with the climate challenge. And that may be the case, but it makes a very big assumption about the cost and scalability of these technologies later in the century. So it's not that that is impossible, but you will find a model is more conservative and also its transition is more aggressive, the less it relies on carbon dioxide removal. The more it relies on it, the more challenging that scenario will be because you aren't able to take as much carbon out of the atmosphere later, which means you can't put as much of it into it earlier. The agriculture, forestry, and land use is sort of a big chunk. And as I said, the models don't do a great job of being really detailed about the specific components. But the key is that in every big transition, agriculture needs to go from being, and forestry need to go from being a source of emissions to a sink. Forests, of course, already are a source, but through land use change and farming practices, the agricultural and forestry sector tends to be a net contributor to greenhouse gases. And the key here is recognizing how fast forests can recover, how much efficient agricultural practices can be spread from one area to another. These are going to be assumptions because this is related to the negative emissions that you see in number 3. But rather than it being an active pulling out, this is a more passive way of reducing emissions, either by reducing the ones you put in or by slowly taking them out through forests. So the levels of assumptions around these will also, as in number 3, relate to how easy or hard it is to hit various temperature and decarbonization goals. So that's really all I wanted to say on the overview of climate scenarios. I wanted to give you a few key variables, a bit of an overview of the new scenarios from NGFS, the fact that there are a number of existing now net zero scenarios that are particularly relevant both from the IEA as well as now from the NGFS. There's some opportunity to go through the polling questions, but I actually think it would be good to just leave about 5 minutes now for questions. So maybe we could take like 2 or 3 questions, and then I want to talk a little bit about next steps moving forward after the conclusion of this session. So as I said, let me take a couple scenario questions. If you want, I'll give you a moment or two to think about those. So one question is, do we need to test various scenarios throughout the process? I think the answer is yes. I don't think there's one right scenario. I think there are scenarios that can be informative, but essentially, in the same way that we wouldn't just look at a single estimate if we were doing a pro forma, we would also not just look at a single, sorry, I didn't mean to advance that. We wouldn't just look at a single pro forma base case or best case. We would look at multiple cases. Scenarios can play a similar role, and scenarios can play an informative role for us in helping to understand specifically what happens when there's a rapid transition, what happens when there's no transition, what about somewhere in between. And I think in terms of the scenario provider, some of them may have more granular data on certain sectors. And so you may choose one that has better coverage, say, of the forestry sector than another. But you'll also want to choose, even for a given provider, a range of different outcomes. I think that's one of the important things, is that there needs to be a range of outcomes that are considered. To what degree does inaccurate data input or model complexity affect the spectrum of projected scenarios? And would minor inaccuracies and assumptions dramatically change the scenario projections? It's a great question. Short answer is it depends. On certain topics, such as physical hazards or long-term forecasts, small assumptions tweaks will have massive implications. So for example, if we assume warming is just a little bit faster, or we assume sensitivity from a given effect is just a little bit higher, those effects can compound over time and result in a significantly different climatic state. This is why modelers that run climate models, why it's so computationally intensive to generate millions of runs, to generate a large number of potential futures and see where they tend to converge or diverge. On the transition side, I think the big X factor, the big question always is long-term projection of economic trends. A lot of these things, the reason that negative emissions had such a big role in some of the earlier models was very simply that if you use a discounting rate for the time value of money, you just take the risk-free rate. If you draw that out long enough, almost any long-term investment is going to be worth very little in its net present value. And what that means is even a very expensive technology will start to look quite cheap if you delay it long enough. It's the same way of saying, well, if you're going to spend $1 million today or $1 million in 2100, you can get back to a net present value for that $1 million in 2100 that is rather small, depending on your assumption. So that's the answer to how big changes can accumulate. On the other hand, there are some things that are relatively straightforward that aren't going to be as assumption driven. For example, if you're using a given carbon budget, so saying we don't want to go over this limit, the speed and scale of energy systems in terms of how they transition, these are things that can be examined in more detail. And while you can make assumptions about them, they also relate to, well, we're not expecting half the cars to come off the road. We can begin to very quickly challenge what maybe seems like a little tweak when it's buried. But when we look at the actual model, we say, okay, well, that is less plausible. So I think there are strong constraints that keep these models on the rails, as it were, for many of the key variables. As I said, there is still high dependency, so it's not, it's not perfect. One question is, do you see scenario analysis as a yearly exercise or a longer term piece that's refreshed intermittently? I think most likely through disclosure mandates on corporations, like those that the EIS and the FCA in the UK have considered, as well as those that the ECB and EBA and the EU Commission have considered in Europe. I think that because disclosure is going to be necessary, then scenario analysis itself will be necessary on an annual basis. Well, stress testing, I'm not quite sure. I think that maybe there's scope for that to be every 2 years or every 3 years. The key though is whether you're using these models for target setting or for something else, it's not the case that the models are static. It's not the case that, oh, well, we set our target with this model this year, that means we have to stick to it. New models will come in and we should be using update, like we should be doing as little forecasting as possible. There's no point to use assumptions that have already proven false, or no point to use assumptions that have been outrun by events. And so these models will recalibrate and will be updated over time. And so our analyses, likewise, we in our different businesses will be in different positions over time as well. So I think that there is probably a yearly cadence from a regulatory standpoint on disclosure, but there's also an expectation that updating will take place in the models themselves.